Welcome back, PlayBASIC programmers. I've just titled this project Blast Processing or Blast Vector Processing. It's basically a variation of what I was hinting at with shapes. It's just doing this job in raw memory though. So in this case here, we're creating a simulation of what the standard particle demo pretty much. So we've got a bunch of particles being emitted. We'll run the demo. I think the other version of this, which does use shapes, this one does not. This is just dot plotting. So we've got our 500,000 points at about 10 frames per second in 165 on my laptop here, which is quite good considering that we're doing manual processing of every dot, right? And the whole point of the best way to make programs in PB quicker is to eliminate situations where the user does a lot of hands-on processing. So, which I was trying to get with this idea about doing addition of vectors. Now, if we hit enter, we can swap modes. Now, what's actually happening is the part that does the addition of the speed vector to the current particle's position is shifted across and done in the background rather than the user doing that operation manually. So we keep a buffer of all the particles in each ring. What we actually got is from this spawn point, we're emitting, in this case, 5,000 particles out from that location, all randomly from that point. So we're keeping the origin. We head down here for the spawning function, keeping a list of these particles. So this becomes a group controller. For each ring that's created, we have a particle count and a bank and a speed bank. This is just buffers of memory, which we're storing vectors in. Floating point, two-dimensional vectors. Got a different thing there as well. Each group has a color for the whole group. They're all the same color. And we keep track of how long they've been updated and what their expected lifetime is going to be. In this case, they're all given a lifetime of 100 frames. So we're using the lifetime to compute what shade of white they're going to be. Just down here somewhere. Yeah, there is there. Sorry, this is processing the lifetime. We're just adding, every time we update the positions, we add 1 to the lifetime count. We just check whether it's time to delete this batch or not. That's returned back to the main loop, and the deletion's done up from the main loop up here. So we're stepping through all the particle groups, updating it. If this group has been in the list for more than 100 frames, we won't draw it. We just fall through here to delete, and then we'll rip it out of the list. The delete just gets rid of the buffers that we've allocated up for it. We could do this in one line, but I just have it in this case. If it's the particles need to be updated, we just keep drawing them. The different aspect of this is that we're using a bank to store each of the individual particles. Now we could use an array here, if people would feel more comfortable with that. The process itself there it is there. So when we know how many particles we need, which is given to the spawn particle up front, I think the default at the moment is like 5,000. So we work out how many bytes a two-dimensional vector of two floats is going to be. We multiply that by the number of particles we need, and we allocate a block of memory in a bank and remember this bank index for later. We do it, that's for our positions or current positions. This is for the speeds of each coordinate. So once the banks are created, they're both empty, they're zeroed out. So speed and position are both 0, 0, so they would be up in the top left-hand corner if we were to leave them like that. So we define position vector. We get a pointer to this positions bank, which is the actual address in memory where this thing actually is. Assign it to our pointer. Now, from here on, that's like a type array. Do the same thing for speeds. So we can refer to position.x, and that will be in array terms, that would be index 0 within, if that was an array. The difference is you're going to manually move to the next one here. So when we step through and initialize the vertices, we're giving the origin point that this entire batch of particles was given. We could just actually copy that into memory, actually, and not do it manually like this, but something else to think about. For each particle, we're just giving a random polar coordinate and a random speed, and setting up the x and y components of our vector, speed vector. Then we're stepping to the next one, just manually stepping the speeds and position across. And we're just looping through every vertex and these buffers we created. So the drawing's much the same, or the update's the same. We just, when we're in manual mode, we just go, okay, how many vertices have we got? Give me a pointer to the position bank and the speed bank. We just run through the vertices one by one and add speeds onto positions, and then move the two pointers forward until we reach the end of our for next loop. Drawing's the same. We just grab our position vector pointer. We do a bit of work here to work out what the color is going to be. Scales between 0 and 1, we just multiply it by 255 to give us an integer range for our RGB level. Here this is our clip range, 0 to 255. So if it's below 0, it'll be clipped to 0. If it's above 255, it'll be clipped at 255. And because we're counting from 0 to the number of frames, and we actually want the inverse of that, we want it to start out fully illuminated, or its initial color, and then slowly die away to black. Yeah, so this alpha mult here is doing, we're taking this grayscale level here and multiply it by our current color, and that will take our original color and give us a scaled down version of that color towards black. We just draw the batch of particles. So that's all the manual processing stuff. That's not the interesting part of the demo. It's this extra bit of garbage here. Over here, we've got a simple. So I made a DLL, got vector 2 type, vector 3 type, a very simple job list structure. So we create. The idea is that you would create a list of these jobs that would be in one buffer, and each job has a source and destination buffer for the data you're using. You can actually give it just standard floats, or 2D vectors, or 3D vectors, or 4D vectors. You're just packing these things. So it's just working either as an individual float, a pair, a triplet, or 4 of them. That's all you're really doing. Here I'm just, have a default here about how many of these job events do you want to create. In this case, I just need one. We're adding the speeds to the positions. That's what we're doing. Create a bank. The bank is sized appropriately for the number of events we want to create and the size of this structure here, this data here. So we're going to pass a raw pointer to the C side to do that, and if it doesn't match, it's going to crash. So we've created a little blast processing data structure. Now we have to fill it in. So we've got this very simple fill-in function here where we've got what bank is the job list, what's the index of the job, what's the source buffer of the vertices or your floating point data, what's the destination that we're writing to most likely, and how many do we want to update. In this particular case, I've preloaded these to work in 2D vectors and to default to the addition. There's 4 modes. You can do a subtraction, multiplication, division. But this is just a bare bones of the test, right? So our actual update code, well, in this execute mode, the update function, all of this part here is not actually necessary. So we're shifting all of that work off until the runtime. We're updating the life counting here. Of course, the draw particles are still just drawn as just dots. All right, back to here. I think the original version of this was called Particle Sprinkler. That uses shapes. And the reason it uses shapes is it does the animation and the plotting with the built-in functions. So we create this randomized shape of vertices, and then we scale it each frame and draw it like that. Now, we'll switch to the blast processing mode. 500,000 vertices. So the bottleneck in this particular demo is actually not the processing of the vertices, it's just the rendering. We're just calling dot a bunch of times, you know. Ideally, it'd be better to have, you know, a dot plot that could do multiple dot plots. Because the dot plots are in clipping, etc. And yes, the buffers are locked, so yeah. Of course the buffers are locked. You know, if you're running at 10 frames per second, that means the frame's taking 100 milliseconds to update. So that's a lot of time. And we're about double. So about 50 millisecond refresh. So I wonder what our frame rate would be if we didn't render dots. If we just didn't draw anything, then we would get a much better metric on what the processing cost of the demo actually is. We'll try it out. So we're in normal mode here and 500,000 points, and we're running at 17 frames per second, which means that a lot of the work is being done, or performance is being lost, because we're doing this manual processing of vertices. We'll switch modes. We're up to 130 frames per second. I think that proves my point. And this is not optimal at all. This is just something I threw together and went, I think that's a better way of doing it. The question is that I do think it's probably better to have a system where the user isn't aware of the data structures underneath, and it just gives you a simple interface, and you can just kind of manually do this, you know, call some functions, do some things to interface, and it lays the data out the way it wants to internally. Anyway, nonetheless, if you want to mess around with it, I'll put this up on the boards, of course, and you can mess around with it all you like. Don't expect it to be documented much, or don't expect it to be actually in any way, shape or form be really thought through. It's just manifestation of the idea. It's interesting how long dot plotting takes, isn't it? So even that, if you was saying before about the drawing stuff, the classic method is you would do something like this, is you would go, we'll have 2 draw loops, and so we might go, I want count, and we'll divide that by 4 minus 1. So, and then here we'll go loop equals count times, loop equals loop times 4. We'll start from here to do the end of those. Sorry, I'm just talking to myself, aren't I? Yeah. What we're going to do is we're going to unroll this 4 times. And the point we're trying to do here is we're trying to remove the looping overhead as much as possible without bloating out the code to an enormous amount. That's reasonable, particularly if we don't have to update it again. And we don't really. How much of a difference will we make? Well, I think we made a mistake with that. If we move off the end of the frame buffer, we will get that. It will break. Normally what I would do is I'd go hunk, right? You see you'd have hunk is this, and then you have leftovers. So count is the modulus of this. It's just the terminology I've sort of quite used to. So we're looping through the hunks, right? And then at the end of this, we do our leftovers. We're going to loop through hunk times 4. Probably don't need leftovers, do we? So if we have 1 hunk, yeah. Loop from here to count, yeah, that's fine. It'll crash, who cares? Who cares? So there we go. Do we crash it? Do we kill it? We're not saving ourselves much time for a little bit. We've maybe won a frame back, considering we're capturing this as well. So if we go to a little blast mode, we're not winning much time back there. I mean, you'd probably have to go. I mean, you could go to fast dot, but you would need to clip the points. So you would need something inside the blast processing routine to give you an idea whether you should draw the dot or not. That would be the best way of doing it, because doing comparisons on 500,000 points, it's going to take a bit of time. Just saying. Yeah. The wonders of software development. But yeah, if you ever wondered about unrolling things, that's pretty much what I'm talking about there. If you switch to fast.dot, you would get crashes because the fast.dot does not check if the dot is outside the frame buffer. We'll just do a quick test on I didn't check this beforehand, so we'll just see if we can we clip it manually and still get the thing to run at a reasonable rate. Fast.dot, yeah. That won't like that, will it? No, that will not like those. Fast.dot doesn't want you to give it floating point. Like even that actually with dot might win you back some performance. Alright, so we read the x coordinate. If we go greater than, just do it, so lower than 800. If we are on the buffer, we have to step forward to the next vertex regardless, so we don't want to do anything untoward with that, so we have to do that. Test our y, 600. What do we got? Look reasonable. We want to loop through all the vertices, so we're not going to do a batch processing this stuff. Quick save, run it. Fantastic, we're running great so far. X, Y, X, X greater than that, yeah. Want to lock the buffer. Am I seeding the buffer or not? I don't remember what optimization caused that. That's always been a source of much irritation. Yeah. Yeah, I would assume this would be slower because we're doing it 500,000 vertice clips. So for vertex are on screen, they're falling through and getting clipped. You'd have, my goal is not to make this all about just dot particles. It's about doing batches of these operations that you might have for all kinds of usages, not just doing things like this. Anyway, that'll do for now. I'll put the example in the forum. It should work with any version of PB actually. So you're welcome to try it out, mess around with it, see what you can get it to do. I don't know. Have fun. Alright. Just to show it's running in older versions of PB. Here it is running in 164p4. So we've got our 500,000 vertices and the rate's down to 5 frames per second. So we're doubling our rate again, but there's so much overhead in the old run time, we're not really breaking through that sort of 20 frames per second barrier. Might try the old learning edition, see if it works on that. Right, here's the learning edition. And yeah, it works in this, straight out of the box. See how low the rate goes. 4 frames per second. Four frames per second. This isn't a 10-year-old runtime. I don't know what year this was released now. So enable the Yeah, I mean, there's a huge update in performance between this is 1.6L and the P revisions. They're pretty much rewritten internally. So even with our DLL doing the workload of all of the vector additions, it's too much for this. We're only clocking 7 frames per second. There you go.